Greetings. My name is Abhishek Yadav, and I'm a student at Fellow Institute of Technology, Chennai. And today I'm going to speak about a topic, digital signature algorithm. So this is my digital assignment 2 for blockchain and cryptocurrency. So let's start. So digital signature algorithm. So the digital signature algorithm, commonly referred as DSA, is a United States federal government standard, or FIPS for digital signatures. So it was proposed by the National Institute of Standards and Technology (NIST) in August 1991 for use in the digital signature standards DSS, which was specified in FIPS 186, adopted in 1993. So a minor revision to this was issued in 1996 as FIPS 186.1, and the standard was expanded further in 2000 as FIPS 186.2, and again in 2009 as FIPS 186-3. Moving on. So, digital signature is basically a way to ensure that an electronic document, let's say an email, a spreadsheet, a text file, or we can say images in of ours, etc., they are authentic. So, there are several ways to authenticate a person or information on a computer. So we need to verify if the message or the data that was sent onto our computer is a valid one. So there are several ways like password. So the use of username and password provides the most common form of authentication that we have always used in C, the most common known use case, username and password. And then we have checksum. So probably one of the oldest methods of ensuring that data is correct. Checksums also provide a form of authentication, since an invalid checksum suggests that the data has been compromised in some fashion. So we add a parity digit or multiple parity digits to a message, and then we send it as a whole to the receiver, and the receiver can use the checksum algorithm to check if the sum is a valid one, and if it is not a valid one, then the user will know who has received the message that the message was tampered with. So this was checksum algorithm. So then we move on to DSA. So we have key generation. So key generation has two phases. So the first phase is a choice of algorithm parameters which may be shared between different users of the system. So the parameters that are like length of the keys and other parameters that will be shared among every node of the system. While the second phase, we compute the public and private keys for a single user. So moving on to parameter generation. So parameter generation. So first what we do is we choose an approved cryptographic hash function, let's say H. So in the original DSS, or like before it was modified, H was always SHA1. So but then the stronger SHA2 hash functions came, and they were approved for the use in the current DSS. So the hash output may be truncated to the size of the key pair. So decide on a key length L and n. So these are the parameters L and n, which is the key length, and these parameters will be shared among the systems. So this is a primary measure of the cryptographic strength of the key. So the original DSS constrained L to be a multiple of 64 between 512 and 1024, and then NIST 800 recommends lengths of 2048 or 3072 for keys, with security lifetimes extending beyond 2010 or 2030 using corresponding longer n. And then FIPS 186.3 specifies L and N length pairs of like 1024, 160 and 2048, 224, etc., etc., for L and N pairs. So this is how like the constraints of the key, the length of the key length evolved. So moving on, the DSA makes use of the following parameters. So first we have P, which is a prime modulus, where P is greater than 2 unless greater than 2 raised to power L minus 1, and less than 2 raised to power L. For L is greater than or less than equal to 512. L is greater than or equal to 512 and less than or equal to 1024, and L is a multiple of 64 like we saw in the previous slide. Also, then we choose a Q, which is a prime divisor of P minus 1, where Q is greater than 2 raised to power 159 and less than 2 raised to power 160. Also, then we have G, which is equal to H raised to power P minus 1 upon Q whole mod P, where H is an integer, where H is constrained as H is greater than 1 and less than P minus 1, such that H raised to power P minus 1 upon Q whole mod P is greater than 1. And also G has order Q mod P. Then we choose a random function x, which is randomly generated, and x is constrained as x, which is greater than 0 and less than q. Then after we generated x, we compute y with the formula of g raised to power x mod p. After we generate y, then we also choose another random, we generate another random variable k, and k is also constrained as k is greater than 0 and less than q. So the integers p, q, and g can be public and can be common to a group of users. So these are the common parameters that will be shared among the different users. So a user's private and public keys are x and y respectively. So a user's private and public key are x and y respectively. So the private key of a user is x, and a public key of user is generated from x using the function g and g raised to power x mod p. So parameters x and k are used for signature generation only and must be kept secret. So your parameter x, which is your private key, and k, which is a randomly generated number that you're going to use for your digital signature, must be kept secret. So parameter k must be regenerated for each and every signature. Then moving on, we have per user's keys. So given a set of parameters, the second phase computes private keys and public keys for a single user. So first phase, we created the common parameters and we shared it among the different nodes in the systems. And in the second phase, we're going to create public and private keys for a single user. So for creating that, first what we do is we choose x by some random method, and x is constrained as it is greater than 0 and less than q. Using x, we calculate y, which is your public key. So y is equals to g raised to power x mod of p. And then your public key is the tuple of p, comma q, comma g, comma y, and your private key is x. So there exist efficient algorithms for computing the modular exponentiations h into p minus 1 upon q mod p and gx mod p, such as exponentiation by squaring. So choose an n-bit prime q. Okay, then n must be less than or equal to the hash output length. So your n-bit prime q length must be less than or equal to the hash output length. So after that, we choose an L-bit prime modulus p, such that p minus 1 is a multiple of q. After that, we choose g, a number whose multiplication order modulo p is q. So this may be done by setting g is equals to h into p minus 1 upon q mod p for some arbitrary h, where h is constrained as h is greater than 1 and less than p minus 1, as seen in the previous slides, and trying again with a different h if the result comes out as 1. Most choices of h will lead to a usable g, and commonly we use h as 2. So the algorithm parameters p, q, and g may be shared between different users of the system, which is also the phase 1 of key generation. Then moving on, we have signing. So let h be the hashing function and m be the message. So first what we're going to do is we're going to generate a random per message value k. So k will be regenerated for every message. So and k is constrained as k is greater than 0 and it is less than q. So after generating k for signing, we also calculate r, which is g raised to the power k mod p whole mod p. And in the likely case that r is equals to 0, we start again with a different random value of a k and we just repeat the steps. After calculating r, then we start calculating s, which equals to k minus 1 into hash function of the message plus x, which is the private key, plus r, which we calculated in the previous steps, whole mod q. So and also the unlikely case where we find out that s is equal to 0, we start again with a different random k, and we repeat all the steps of like r generation and s generation again. And then once we get the values of r and s, we know the signature is created, and the signature is the tuple of r and s. So the first two steps amount to creating a new per message key. The modular exponentiation here is the most computationally expensive part of the signing operation, and it may be computed before the message hash is known. The modular inverse k minus 1 mod q is the second most expensive part, and it may also be computed before the message hash is known. It may be computed using the extended Euclidean algorithm or using Fermat's little theorem as k raised to power q minus 2 mod q. Again, moving on, we come to the example of like how we create a private key and public key from a set of DSA parameters. So first we obtain the DSA parameters. So see, getting the digital signature algorithm DSA parameters of a key pair. So this is the pseudocode of that. So we have big integer p, big integer q, big integer g, we have x, and we have y. So we have all these integers or parameters, we can say. And what we do is first we create a DSA key factory, and in the key factory what we do is we get the instances of the DSA parameters that we created. Then we create the DSA private key spec. So private key spec, we give it the parameters of x, p, q, and g, and using the private key spec we then generate the private key from the key factory. So similarly, just like we created private key, we also do the same things for public key. We first create the key spec for the public key, and using the key spec, then we create the public key. And after that, we for like some error removals, we can also use some exception handling that you can see that I've wrote in the pseudo. So coming to the example. So first what we do is we compute r is equals to g raised to power k mod p whole mod p. So then after computing r, we compute s, which is equals to k minus 1 into x into r plus I whole mod q. And after that, once we have calculated the values of r and s, then verifying a signature. So for again I is the input and r comma s is the signature. Tuple of r comma s is the signature. So using these parameters, we calculate ui, which is basically s minus 1 into I whole mod of q. We calculate u2, which is s minus 1 into r mod of q, whole mod of q, and then we calculate v, which is equals to g raised to power ui into y raised to power u2 whole mod of p whole mod of q. So after we calculate u1, u2, and v, we check if v is equal to v equals r. If v is equal to r, then we can say that the signature is a valid signature, and it is the message is not being tampered with. So this is how we verify the algorithm. So if we can first reject the signature if r or s is not following the constraints that s and r are greater than 0 and less than q. So after that, for verifying, we can use this. So we first calculate w, which is basically s minus 1 whole mod q. Then we calculate u1, which is hash function of m into w whole mod of q. Then we calculate r2, which is r into w whole mod of q. And then using u1 and u2, we calculate v. And if the digital signature is valid, if v is equals to r. So this is how we verify digital signature, and DSA is very similar to L-Gamal signature scheme. So DSA is very similar to this. So correctness of the algorithm. The signature scheme is correct in the sense that the verifier will always accept genuine signatures. This can be shown as follows. So first, if G is equaling H into P minus 1 upon Q whole mod of P, it follows that GQ HP1 in 1 mod Q by Fermat's little theorem. So since G is also greater than 1 and Q is the prime, G must have order Q. So the signer computes S is equaling K minus 1 into hash of message plus XR mod Q. So thus K is equals to hash of message into s minus 1 plus xr of s minus 1, which is basically hash of message into w plus xr w into mod of q. So since G has order Q mod P, we have GK as G into hash function of message into W, GX RW, and then we can come to a conclusion that it is G raised to power UI and Y raised to power U, which into mod P. So finally, the correctness of DSA follows from R is equals to GK mod P whole mod Q is equaling G raised to power UI, Y raised to power into mod P whole mod Q is also equaling V. So, and finally, I would like to talk about the sensitivity of this algorithm. So, with DSA, the entropy or secrecy and uniqueness of the random signature value k is very critical. So, the random value k that we use for every unique message, we generate a random value k is a very uh, critical and unique key. So it is so critical that violating any one of those three requirements can reveal your entire private key to an attacker. So your entire private key to an attacker will be revealed only if a certain uh, bits of your cape is revealed. Even if such small bits are revealed, your private key can be hacked by an attacker. So using the same value twice, even while keeping k secret, using a predictable value or leaking even a few bits of k in each of several signatures is enough to break TSA. So with that, I would like to conclude my presentation, and I would like to take my thanks, and I would like to take my leave and say thank you.